So far we've seen a differential drive car, we've seen manipulators, we're going to look at quadcopters, but in general, these machines have to go from point A to point B, okay? And there might be obstacles. So these are obstacles. And clearly you can do this task to go from point A to point B in multiple ways, right? So here is one path. There is this path, which is probably more safer. So you don't really bump or come anywhere close to the obstacle. You could also do something which is sort of like this. Okay, and one might argue that one is better than the other. So for example, the blue line, which I just drew, is very jerky in the sense the robot has to go straight and then suddenly change path. So clearly that's not desirable. So when we want to get a robot to go from point A to point B, we might want to think of what are we trying to optimize for. So it could be energy usage, it could be the risk. So the black path is probably more riskier than the red one, but the blue one is more jerkier. So you could have different metrics to find that path, right? And so what is clearly important here is how do you optimize a path? So optimization is kind of central in robotics. We always try to do something in robotics which achieves certain goals. Okay, and then could be multiple criterias. So you could have a formulation where you could minimize the energy as well as the risk and so on. So we'll not get into too much of that, but I would uh, show you simple implementations of optimization. But before we do a trajectory optimization, we need to understand what exactly optimization is. So I'm going to motivate this with really simple examples of optimization. So let's start with unconstrained optimization. So example would be going from point A to point B when there are no obstacles, no constraint on how much fuel you can use, but we want to minimize something. So here is a function, okay? This is now just a sort of optimization class, not really too much into robotics. How do you optimize? Sorry, let me use a different function. Let's say optimize or minimize rather x2 minus x1 square, the whole square plus 1 minus x1 square. Hold on, let me check that. Okay, got it wrong. Just write it like this. Okay, so the way to write this is minimize f of x, where f of x is at, and then what are the optimization variables where they are x1 and x2. So this is how you write an unconstrained optimization problem. And there are many methods to solve it. One of the things which really comes to my mind is why don't you graph f of x versus x1, x2, and that will be some kind of a surface, right? It's be some surface, and so that's a surface. And hopefully it will give you some point at which this is corresponds to the minimum. So you can graph it and then eyeball to find the optimum. And then, once you have a ballpark, you can then say, you can then do some checks to figure out what that minimum is. So that's one way, graph. Another way is to actually guess, right? And we do this all the time in engineering. We want to guess solutions. In this particular case, okay, question. So for the objective function, how to make the equation, or rather how do we get the equation? Okay, so the equation is usually specified in terms of things of interest. So fuel consumption, for example, there's a formula for how fuel is used in a car or a quadcopter or battery discharge. Time is easy to formulate. So this is something which will be given to you, or as engineers in real field, you'll have to come up with the objective. So we'll get to that in a bit later. Right now, we're just trying to understand how to do optimization. Okay? So we could guess. And there is something about this particular equation which makes it easy to find the optimum. You can see that we have two square quantities, okay? And when you have square quantities, the function f of x can only be positive because it's sum of squares. So this function achieves its minimum when each of those things in the bracket, which are squared, are equal to 0. So we might say that 1 minus x1 is 0 is when the second equation equals, or the second part in that f of x equals 0. So x1 equals 1 is probably when the second part of f of x is minimized. And then if you put that in the first part, we get x2 minus 1 square equals 0. And so x2 equals 1. So we can say that x1, x2 equals 1, comma 1 minimizes f of x, right? You can see that when you put that, you actually get f of x equals 0. 1 comma 1 is 0, right? And that's actually the minimum of this. And we could guess this solution because f of x had this very special form. But in general, it's very hard to guess or graph these things. And so you want to use a numerical package to do this. So I will not get into the details of how to do this computations. I will only show you how to formulate the problem and then use MATLAB to solve it. So the third method is numerically solving for the optimum. Okay, so the graphing method only works for low dimensions, right? For 1, 2, and up to 3 dimensions. Once you get beyond 3 dimensions, it's simply impossible to graph. The guessing works only for special cases, right? So in this case, we saw that it was a special quadratic function. In fact, it was a sum of squares, and that was easy to optimize. But numerically solving for the optimum works almost always. Okay, with some caveats, but it has more places where it works than the other two. So we will see how to numerically solve for the optimum. Okay, and so the function which is used in MATLAB to solve unconstrained optimization is called f min unc. Okay, and so we will see how to use f min unc. Essentially, f min unc, what it requires is you need to give it the you need to give f min unc the function f of x, and you need to tell it what are the variables it's optimizing for, in which case it's x1, x2. The syntax for f min unc is something like this: x f val exit flag equals f min unc at the name of the function, which is, in this case, it's going to be f, and then the variables. So x, so you need to give an initial guess, that's x0. And then if you want, there are options, which I will talk in a bit when I code this. So this is the syntax, this is the objective, this is the optimization variables, this is the solution, this is the optimized value. So for this case, when we solved this, the function I wrote down, the value was 0, and that will come up when you do fval. And then this gives some information about the solution, okay, whether it converged, it had difficulty solving, and so on. Okay, so let's see how to program this in MATLAB. So let me switch screens. Same problem I wrote down, and one thing which I find which is really hard sometimes for me when I'm learning something new is to stare at a blank screen and then try to code it from scratch. And the way I like to do things is I like to copy down examples from MATLAB and then modify them to suit my purpose. So what I'm going to do is I'm going to just search for help f min unc. and then hopefully there will be an example which I could use. So this is the documentation, as I said, helps you to get the information about the function. I wrote down the syntax earlier, so I'll not delve more into that. Let me just try to see if there's an example they solve. So it looks like here is an example. Let's just copy this. So let's call this function test f min unc. Clear the screen, clear all variables, and then let's just close all the figures if they were open. Let's save that file. So test, this is, we have a file, let me go fmin1. Okay. Okay, so now I'll just copy this. Okay, so this is optimizing some function f equals sine x plus 3. We run this, and then it says that the optimum is 4.7124. Anyway, so we got something working, and now it's actually quite easy to modify this to suit our purposes. So let's see if we can modify the code to suit our purpose. So let's define the function as I wrote it down. So that's x2 minus x1 square plus 1 minus x1 square. Sorry. And what's x1, x2? Well, they'll be actually coming from x. So the first variable is x1, so x1, and x2 is x of 2. Okay, so I got that. I need to give an initial guess. That's actually this one. So that's, let me call that x0. Here x0 was 2, but in this case we have two things, two variables. So we need to initialize two numbers, one for x1, one for x2, and so I think that's about it. Let's try to run this. Okay, so it solved the problem and gave me 1, 1. Let me put down the other things which I mentioned here, but in my notes, but I did not quite put them. So that's the fval and exit flag. Let's run this again, and then we see that we get there's local minimum found. It completed. The x was 1, 1, just like we guessed. The value of f at 1, 1 is very close to 0. This e raised to negative 11 indicates it's 10 to the power of negative 11. And then exit flag is just something which tells me if it converged to the solution or not. Exit flag 1 generally means it's had no difficulty converging to the solution. So you can actually get more information about these things by typing the documentation for fminunc. So if you scroll here, it says exit flag. These are the values for exit flag. One is this literally means that it converged. 2, 3, 5, I'm not too much worried about. They are normally good. Anything -1, -3 are not good, and that means it did not converge. So last thing I wanted to show you was how to put options. So there's this options. Let's see if we can put options. And so what are the options? The options are how much do you care about the optimization in terms of accuracy, or how many function evaluations. What is function evaluation? It's basically evaluating this function. How many evaluations do you want to give the optimizer to use? And those things are embedded in options. So let's see if there is an example of MATLAB showing the use of options. Okay, there it is. So let's just copy this. Put it here. And how do we use it? Well, this example here shows that you can put options as the third argument. So let's just put it here. Okay. Now, if I run this, it's going to complain. And it complained because here we say we want to specify the gradient, and we are not specifying the gradient. The gradient is basically the Jacobian we've talked about. It's the rate of change of f with respect to x. So let's remove that. Okay, and now it should work fine. Yeah, but if you want to specify more options, then you want to go over to the internet and then say MATLAB fmin options. This is just because the example did not give me options listed. So I thought I should just go to the internet and find what are the options. So here are some ways options is used. So this is basically specifying the algorithm, then the gradient, which we don't want to set. So here's another example. But if you want to really find what options are, we can look at the documentation. So it says options, there's algorithm, check gradient. So these are the various things you can specify. Let's say display, that's the one which I normally use. So let's see what this does. So if you say display iter, then and run this, what we will see is it actually tells you how it arrived at the solutions, telling you what it's doing at every step. Okay. Then if you want to explore other things, let's see. Max iterations, this tells you how many iterations are allowed. So how many times it can use the solver to come to the solution. And the other one which I usually like to use is the, let's see, the function evaluations. If I can only find it. Okay, max function evaluation. So max function evaluations is a maximum number of evaluations. So what I'm going to do is I'm just going to put that, and as the name sounds, it's going to be a number, right? It's not going to be like iter. So I'm going to put, let's say, okay, you can see here actually, you can see this func count. That func count is basically the number of function evaluations it used. So that's 78, right? So if you limit this to, is there somebody doing that? Okay, 75. And then if you run this, so you see it stopped at 75 evaluations. Okay, so, and you also see it's actually complaining. It's saying that solver stopped prematurely. So usually you want to put big values for this, 100. Usually people put 1,000. And I'll tell you why this is important. When you're running something like this online real time, you don't have too much time to do a computation. So you can actually limit the function evaluations to a set value. That way, the computations can take place in real time. And that's probably one of the places where people use this. Okay, any questions about anything so far? Okay, no questions. Okay, let's go to fmincon. What's the difference between iterations and evaluations? Okay, good question. So this is the iteration, this is the evaluations. Iteration is basically what the solver is doing, and this is something you want to, I'm not expecting you to know this, but this is to do with the algorithm that fminunc uses. It basically has a method in which it does some calculations. Okay, so for example, here at the 0th iteration, it evaluated this function 3 times. So it could be evaluate that functions to find things like the Jacobian, or sometimes this the higher thing, which is called Hessian, which is the second derivative. For the second iteration, it used 12 evaluations. So it's basically using f to do some computations, and that really depends on the algorithm you use. And so that would be sort of beyond this class, but I would encourage you to look at the documentation. It actually tells you more than what I just told you here. So if you try to see the algorithm, so it uses the 2 algorithms, quasi-Newton and trust region. If you actually see the documentation, it actually tells you how this is exactly the problem I solved. It actually tells you what it was doing when it was finding the solutions, and the iterations and all. You can learn more about it over here. So there's a method called line search. There's a method called radial. It's not there here. Okay, so it just uses line search. So I would encourage you to read this if you are interested more in optimization. So optimization is a field which has got so much prominence in the last couple of years, and that's because computers have got faster, and there are better and better methods, and there are people whose job is to do optimization, and optimization is very generic in terms of its applications. Not only robotics, there are people on Wall Street using it, people in logistics using it. So it opens a lot of jobs if you're interested in pursuing optimization. Okay, so what problem I'm going to solve is a simpler problem before we get into more complicated ones. So let's say minimize f of x equals x1 square plus x2 square plus x3 square plus x4 square plus x5 square. So this looks very similar to um, unconstrained, right? So x equals, if you like, x1, x2, x3, x4. Okay, let me just minimize x, where x is x1, x2, x3, x4, x5. Okay, so if that was a problem, that's very easy. But most of the time you have constraints. Like, for example, you can only accelerate your car up to so much, right? You can't accelerate like crazy. You cannot. Uh, you have let's see. When you're going along obstacles, your car has certain dimensions, so your car cannot hit or pass through one of the obstacles. So there is that constraint of configuration, and so I'm going to write a few constraints here, and this is for this fictitious example. So my solution has to lie on a line described by this equation. It's actually a plane because it's three-dimensional. And then it should also satisfy this equation, x squared plus x4 equals, sorry, x3 squared plus x4 equals 2. And then x1 should always be greater than 0.3, and x3 should be less than 5, and then x4 square, or x4 square plus x5 square should be less than equal to 5. Okay, now this problem looks very intimidating because, well, first of all, it's in 5 dimensions. There's x1 all the way to x5, and then there are these constraints, and so there's no way you can graph this. You cannot also guess in a solution, right? Because you have these constraints. And the only way you can solve this probably is to use some numerical method. And the numerical method we'll be using to solve this is based on constrained optimization in MATLAB, is called f-min constant. This is a function which does constrained optimization. Within this function, there are multiple methods you can use, and I can get to that a little bit later when we're doing the coding. So what f-min con expects you to do is, it expects you to formulate the problem in this fashion: min f of x, where x are the decision variable. You need to put the constraints in this form. We need to put bounds on x. We need to put bounds, well, we need to put all the equality constraints as, so these are what are known as linear equality constraints. They're called constraints because they are, you have an equal to sign, and they are actually known as equality constraints. And then because there's only x and no x squared, there are linear equality constraints. And then we have what are known as inequality constraints. So ax is less than b. So these are linear inequality constraints. Okay, so that's not where it ends. You could also have constraints which are non-linear, and you just put them as c equals 0. Okay, so these are non-linear constraints. So non-linear, the right way to say is non-linear equality constraints. And then we also have non-linear inequality constraints. So non-linear Okay, so once you specify the problem in terms of these 6 things, you're all set. Okay, and so what I'm going to do next is try to take the problem which I specified and put them in this form, And then once that's done, it's ready to go into MATLAB. Okay, so that's how the problem formulation takes place. So let me copy this in the interest of time. So let's try to put that in this form. Okay, so first of all, I need to specify the lower and upper bound. We see that from these two equations, this specifies some bounds on x1 and x3, and the remaining variables are unbounded. So what I need to say is x1 is between 0.3, that's the lower bound, and then infinity is its upper bound. For x3, we have the lower bound is minus infinity, and the upper bound is 5, right? So I've taken care of these two, so I don't have to worry about them. The other ones, x2, x4, x5, are actually unbounded, which means that they go from minus infinity to plus infinity. Okay, so these are my x between LB and UB. So that's taken care of. Okay, next, let's try to see if we have equality constraint like linear equality constraints. And we see that that happens over here. So I need to write it in this form. So what I'll do is I'll write x is basically x1, x2, x3, x4, x5. Okay, and since there's one equation, A would only be one row and 5 columns. So we have, there's one coefficient of 1 for x1, so 1. For x2 is 1, x3 is 1, and then x1, x5 here are missing, so that'll be 0 and 0. So when you take this matrix A equals, multiply with x, you should end up with the right-hand side, which is 5. So this is basically specifying the linear equality constraint. Okay, and then finally, we have you can see this equality, you have a non-linear equality constraint. So C equals 0, and that's basically this one. So I'll write it down. That's going to be x3 squared plus x4 equals 2. And then I'm almost done. I just have to write the last one, which is C less than 0, which is the nonlinear inequality constraint. So that's x4 squared plus x5 is less than equal to 5. So I'm missing one, right? I'm missing A, x is less than B. This is not there in this formulation. So what you do is, in MATLAB, you just say A is the null matrix and B is the null matrix, and we can input this. So what we need to give MATLAB is f of x, which is already here, and then we need to give it the lower and upper bound and all the other inequality equality constraints. So let's just do that in MATLAB now and see what we get. Okay, so any questions about anything so far? Min con, okay, and so essentially the framework is exactly what I've written down. So there's a call to fmin_con, and fmin_con has these arguments: the initial guess, which is I put some random guess, but it needs to be 5 numbers. There's A, there's B, the equality, and then I told you there's no linear inequality constraints. So that's just the null matrix, and then A equals, B equals, and then we have the bounds, lower bound, upper bound, just exactly what I put down there. And then what is missing here is probably the equality inequality constraint. Those are sitting in this function called non-linear non-LCON. Okay, and the way that function is written is it basically outputs the equality and equality, non-linear equality and inequality constraints, and that's basically right from the way I written it down. And then that's the cost. We'll run this. and then it basically does that in probably no time. So it displays the progress of the optimization, tells me the solution, gives me the minimum value, which is 8.4142, and then exit flag 1 means that it converged. And